Hey everybody, welcome back to your lecture number 12. This is going to be on sedimentary rocks, sedimentary structures, and continuing our discussion of sedimentary rocks. So we'll be moving right along here, and hope you got your lecture assignment packet number 12. Here, I got mine. So we'll be going over this. I'm really focusing a lot on clastic rocks today. So I kind of gave you an intro to sedimentary rocks last time, but now we're going to be kind of looking in, zooming in on the clastic sedimentary rocks and learning a bit more about what you can learn about. This is a great picture, by the way. This is the called the wave. It's a good name for it, right? And this is in Arizona. And it's actually really hard to get to, and they only allow a few visitors to this place a year. So you kind of have to enter a lottery to actually get kind of tickets to go and see it. So go and visit it. So anyway, it's a very, very, very famous rock structure, though, made of sedimentary rocks. And actually, these are cross-bedded sandstones. That's what these are. So let me get my pen out. There we go. And we'll be moving along here. So today we're doing more on clastic sedimentary rocks. Remember, clastic sedimentary rocks are rocks that are built up, sedimentary rocks that are built up out of clasts, out of little broken pieces of grains, of minerals and rocks, right? So this is a really obvious one. This is, by the way, I hope you remember, this is a breccia. Okay, so it's made out of an assortment of kind of like pebble-sized clasts, but also sand and clay and silt and other stuff too. So anyway, and you can see that because they're angular, we call that a breccia versus a conglomerate. Okay, so we're going to be focusing today on the shape, size, composition, distribution of grain size in a clastic sedimentary rock, and what that can tell us about the conditions under which it forms. So we can get so much information about how, like, the environment and how the sedimentary rock formed by looking very closely at the size and shape and distribution of different grains. Okay, so clasts, just a little review of clastic sedimentary rocks. They're formed from lithified clasts. Clasts are just rock fragments or grains, particles. They're just the little pieces of broken rock and mineral from which the sedimentary rock is built up out of, right? And you can have really fine grained clasts like mud. You can have kind of medium like sand, or gravel or pebbles can be coarse. When you get mud lithified, it undergoes diagenesis and lithifies, you get mudstone or shale. When sand lithifies, forms sandstone, and when gravel and pebbles lithifies, it can give you things like conglomerates or breccias. Okay, this is a really, I don't know if you can see this picture very well. This is a really cool countertop made out of a conglomerate. So remember, it has all the big pebbles, cobbles, gravel, things like that. So anyway, so this is what we're going to talk about today. We're going to talk about what the clast and grain size tells us, what the angularity or sphericity, like how angular or spherical the grains are, what that tells us. We'll talk about the degree of sorting, and we'll talk about the chemical maturity. Okay, so all these things we're going to take a look at today. Okay, so the first thing is the grain size. All right, remember, we can have really fine grained material, okay, so really fine grained particles, medium grains, or coarse grains, right? So this is maybe stuff like pebbles or cobbles. This is stuff like sand. Maybe this is stuff like silt or even clay, okay? What that tells us about is the energy of the environment. The energy of the environment. So, what does that mean? That's what number 2 says on your lecture assignment packet. What does the energy of the depositional environment mean? What does that have anything to do with? So that means it's, I'll kind of explain it like this. The energy of the environment has to do with how powerful or how fast the water was moving that deposited it. Remember that all these clasts are being deposited by either wind, water, or ice, okay? Now, water, for the most part, is the dominant medium that's transporting grains. So this really, energy only applies to the water. But give you an example. This would be a high energy environment, right? A swift moving mountain stream, that would be high energy, okay? So I want you to take a look at this picture. High energy, mountain stream, it's moving really fast. What do those grains look like? the sediment grains that are in the stream bed. Take a look at them. You can see them, right? They're big boulders, big rocks, cobbles, gravel, boulders. That's what you see, right? Why is that? It's because clay and silt and sand, the water's moving so fast, it has so much energy, it's just going to sweep that material downstream, and it's going to be deposited somewhere else, right? That fast-moving water is going to deposit that material somewhere else. And what gets left is the heavy stuff that the water cannot carry. Boulders, gravel, cobbles, stuff like that, okay? So if you go to a fast, high-moving stream, or maybe you go to a beach that has lots of big waves. We don't have big waves in Corpus Christi, but if you go to like the Pacific coast where there's big waves splashing, there's a lot of energy. What do you find? You find these pebbles, cobbles, things like this that you see up on the screen right now. So what kind of sediment would you find in a fast-moving stream? You would find cobbles and things like that. If you ever think of like river rock, you ever go to like Home Depot or something, you see river rock for sale, right? You find, what's river rock? Where they're like big cobbles, right, of rock that you would find in a fast-moving river, okay? That's high energy. So when cobbles like that, river rock, lithify, what does it make? It makes a conglomerate like this, right? So it becomes like a conglomerate. Other things can make conglomerate too, but that's one example. Here is a picture of a low energy environment. Just like you see this like placid lake, right? No movement, no, just totally glassy water. Okay. Here in Corpus Christi, you might think of like our back bays. So like once you get like back away from the wave action, you get all these bays, right, that are tidal flats and things like that. Very little water movement there. Sometimes the water is very clear and glassy there. There's no movement. You can get really fine-grained material. So you know that lakes and ponds often have very muddy bottoms, right? Like, a lake like this, as beautiful as it is, it may not be very much fun to swim in, because if you try to walk into it, what you're going to get? You're going to get... Hi, sorry. I was recording during my office hours, and then somebody came by, but I paused it. So anyway, he's gone now. But anyway, low energy environments. Where was I? So, if you step into a lake like this, you can maybe imagine swimming in here. What do you expect to find? Imagine you're here at this lake. You're going to go in for a swim. What would you expect to find on the bottom? Do you think you're going to find a whole bunch of like big boulders and cobbles? Probably not. You're probably going to have a bunch of mud, right? So you might step into it, and probably some of you here have maybe gone around the back bays in Corpus Christi, and you try to step into the mud there, and you go sink up into your knee, right? And so things like that happen all the time. So you probably know that lakes, ponds have muddy bottoms, and it's because they are low energy environments. The mud is that really fine particulate matter, right? So if the water's moving really fast and it's high energy, that small particulate matter, like the clay and the silt, that can't settle out. It gets carried away by the water, the fast-moving water. But when the water slows down, then all that silt and clay can settle to the bottom, okay? So that's what happens. Now, what does this tell you? It not only tells you a little bit about what the energy of the environment is, it also tells you how far sediment has been transported. Okay, when sediment starts off in the mountains, here you have like these mountain areas that are being eroded, right? So this is erosion happening here and weathering. That particulate matter gets carried out of the mountains down towards the mouth of the stream. And what happens is that as it gets bumped and moved along the river bottom, it gets broken down. And usually what happens is as you move further and further and further away from the source of the sediment, i.e. these mountainous regions, you move further and further away from the source of the sediment breaks down into smaller and smaller particles. Now here in Corpus Christi, there aren't a lot of mountains around like this, like these areas where there's going to be a lot of sediment production. Okay, those mountains are, you might know, the hill country, right? That's where like our sediment maybe is coming from here in Corpus Christi. So all that stuff gets eroded. It's far from the source. It's like a 3-hour drive, right, to get to there. So it's hundreds of miles away, 100 or 200 miles away. So you have to transport all that sediment really far. And by the time it gets down here to Corpus Christi, it's very small particles of sand, silt, and clay, mostly silt and clay, right? So that's what actually reaches here. And that's why, you go around Corpus, you have all this clay soil and silt and stuff like that. So sediment grains can also tell you about distance of transport, okay? Can tell you about distance of transport. Number 3, for classic sedimentary rock, how can you infer the energy of the environment? It's from the grain size. Okay, grain size will tell you what the energy of the environment is. And what do class sizes tell you about classic sedimentary rocks? It tells you how far the sediment's been transported, and it tells you it tells you also what the energy of the environment was, the depositional environment. Okay, so sediments bump along rivers, waves, wind. They break up. They become smaller as they get transported further and further and further. Okay, so this is what stuff far from the source looks like. Okay, and this is actually a picture. It could be Corpus Christi, right? It's far from the source. Look around. Do you see any mountains here? No mountains, right? So the sediment has come from far, far, far away. Okay, but look at here. Close to the source, you see these mountains here. I shouldn't say mountains. They're not mountains, but these cliffs, right? These are eroded cliffs. And you can see that the sediment is very big and cobbles and boulders and stuff. Well, that's because it's close to the source, okay? So that's what grain size tells you. Now, the next thing we're going to talk about here is angularity and sphericity, okay? So number 5, what does angularity, sphericity of the class indicate about the sedimentary rock? Here you want to think about a rock tumbler, okay? A rock tumbler. What happens when you put something in a rock tumbler, right? Maybe it starts off like this, but after a while it ends up smooth and smooth and round, right? So it's the same thing when rocks and sediment are tumbling along the bottom of a river or some kind of, whether they're being transported by wind or ice or glaciers or whatever. They're being tumbled along, carried along, and they get smoothed out over time. Okay, so it tells you how far the sediment has been transported. When you have very angular grains, it means that you're close to the source of the sediment. When you are very spherical, it means that those grains have been transported very far, and that sediment is far away from the source of it, from its source. Okay, so if you look at this talus slope at the base of a cliff, take a look at the sediment here, the boulders here. Very angular, right? They're very angular. These aren't well-rounded, okay? Why aren't they well-rounded? Because they're very close. They've just broken off, and they have all these sharp edges. They haven't been transported very far and lost their sharp edges. If you want soft edges, you have to go far away from the source, okay? So, as class are transported by wind and water and ice, they're tumbled and smoothed out, right? So like I said, think of a rock tumbler. As it moves and turns the rocks over in the river, it smooths them all out. So if you go to a river and a lot of those rocks are real nice, right? They're like been naturally tumbled out. So that's what sphericity, angularity tells you. It tells you how far that material has been transported. Okay. All right. Now, what does number 6 says? What does a poorly sorted sedimentary rock look like? We're going to talk about sorting now. Sorting is another important aspect here. So sorting is how, what does the distribution of the different grain sizes look like? You can have a poorly sorted rock like this. You'll notice if you look at this picture, this sediment is poorly sorted. That means that there's all sorts of different grain sizes there. Okay. You could have something, on the other hand, that is well sorted. If you take a look at this sediment, you'll notice that every sediment class is about the same size. That's well sorted. This one is sort of medium, and this one is poorly sorted. Okay. And this over here is well sorted. Sorting can tell you two things. Okay. Well, first of all, let's answer question number 6. What does poorly sorted sediment look like? It means that it has a whole bunch of different grain sizes. Everything from clay to sand to silt to cobbles. Perfect example of this is a conglomerate or a breccia. Those are poorly sorted clastic rocks. On the other hand, a sandstone or a shale, siltstones are often well sorted. Not always, but often well sorted. Sorting tells you how the grains were transported. Okay, so there are a few things that sorting tells you. You have I'm hitting the microphone with this thing. Number 7, what does the degree of sorting indicate about the sedimentary rock? Okay, tells you two things. The first thing sorting tells you is what kind of medium has transported this rock. So whether it's ice or wind or water. You can get some indication of that from the degree of sorting. Here's a beautiful breccia. Okay, why is it a breccia, not a conglomerate? Look at how angular the grains are. Do you see the angular pointy edges here? That means it's a breccia, not a conglomerate. A conglomerate's going to have nice, well-rounded edges. So what do you think of the sorting here? Well sorted or poorly sorted? I hope you're saying poorly sorted, right? Because you have big grains, you have little ones, you have big ones, you have a lot of stuff that's in between, like clay or silt that's in between the big gravel clasts. What do you think about the energy environment? What do y'all say? What would you say the energy of this was? Probably pretty high, right? Because you have big class sizes in there. What would you say about the distance from the source? Okay. We have high energy, big clasts, poorly sorted. What do you think about the sphericity? Angularity, sphericity. Highly angular, right? What does this all say? What's the takeaway here? This is very close to the source. So the distance from the source is close. Okay? How do we know that? We know that from the large clasts, the angularity, the sharp angles of the clasts, and the size of the clasts, which are large. Okay, and we know it also from the sorting. So there's a lot of indications here that this rock really just broke, the gravel just broke off of a talus slope and got lithified. Okay, take a look at this guy. Here's a conglomerate. You notice how the big gravel pieces in this are more like round. They're rounded. Okay, they have softer edges. What is the sorting? What do y'all think? Sorting is poor, right? What is the energy of the environment? Probably high. Okay. What do you think about, and why do we think it's high? It's because the grain size is large. What do you think about the distance to the source? It's probably pretty close. Further away than the breccia, but still relatively close to the source. Here's a question for you all. I just want to, these are good questions to test yourself, because you can easily on the test, the exam, midterm or final, get a picture like this. And it'll ask you, what's the grain size? What's the energy of the environment? What's the distance, do you think, to the source? Tell me why you think so. Okay, so you need to be able to do things like that. Look at a classic sedimentary rock and analyze it. So the distance to the source is probably close, but it's probably further away from the source than the breccia. Why? Because the grains are rounded. Okay, that means they've been tumbled and transported some distance. Okay. On the other hand, here's a well-sorted sandstone. Okay, all the grains are the same size. So what's the sorting? It's well-sorted. Why do I say it's well-sorted? Because all the sand is the same size, right? You don't see any big chunks of pebbles or gravel in this. They're all just little sand grains. What do you think of the energy of the environment? It's probably medium, right? What do you think about the distance to the source? It's probably kind of a medium distance, a medium degree of transport, maybe a high degree of transport. So I would say far, medium to far. Okay. So transport sorts the grains. Okay, so one thing that sorting tells you is how far the material has been transported. Sorting occurs through transport. So as things are carried away by the wind, the ice, the water, it will naturally sort those grains out. Okay? So, for example, the sediment here at the base of a cliff is very poorly sorted because it's not undergone any kind of transport except maybe just gravitational, falling down a slope. So it's very poorly sorted. You get clasts of every size here. On the other hand, these sand dunes, take a look at these sand dunes. They're well sorted because they've undergone a lot of transport. Okay, the mountains that this sand originated from are far away. We don't know where they came from. It's far away. Okay, so sorting tells you the degree of transport, but it tells you something else too. It can also tell you about the medium of transport, whether it's ice, water, or wind. Wind is very, very good at sorting sediment. Sand dunes, if you go to a sand dune, what do you find in a sand dune? Do you find clay or silt or boulders or pebbles? No. You only find sand. It's very well sorted. Why is it very well sorted? Because maybe it's undergone a lot of transport, but also because it's been transported by the wind. And wind is very good at transporting. Very good at sorting. Wind is the best at sorting, and it forms sand dunes. It can also form things called loses, which are dunes made of silt instead of sand. Okay. Water is kind of okay at sorting. It can sort, but it's not the best. Okay, so water can sort out things, can make, obviously can sort out sort out silt and clay and sand. But the worst sorter, the thing that does the worst job at sorting is ice. Ice, glacial ice, and we're going to see, I know this is a weird idea, but I'm going to tell you right now, glacial ice moves just like a river. It flows, it moves, and when we talk about glaciers, you'll see this. I'll show you lots of movies about time-lapse films that show you, and it's going to blow your mind. You're going to be looking at this glacier, and it looks stationary, but when you do a time-lapse photo of it over the course of months, it's flowing like a river. It flows just like a river. Ice flows, glaciers flow, and they pick up sediment, and they are the worst at sorting. Glaciers, like this little video here is showing you, they pick up all sorts of things. They flow downhill, and so it does flow, it does move, and it transports sediment of all sizes. And it can be, this is actually a really good example. This is glacial till. This is a picture of glacial till. And you can see this is the sediment that gets picked up by a glacier. It's everything. It's sand, it's silt, it's clay, it's boulders, it's cobbles. Everything gets picked up. In fact, sometimes you can have huge boulders that are picked up. The size of, look at this. This is so crazy. Look at that boulder. That boulder, that tiny, little person right there, right? Show you the size. That boulder got picked up and carried by glacial ice. That's called glacial erratics. Okay. Massive boulders, the size of a school bus, can be picked up by glacial ice and moved. Okay, so huge things. And glacial ice can also pick up silt and clay. It picks up everything. It does the worst at sorting. Ice is the worst. So sorting tells you about distance of transport, but it also tells you about the medium of transport. Very poorly sorted sediment could be a glacial deposit. Could be formed from a glacial deposit. Very well sorted sediment could be well sorted because it was formed by wind, a wind deposit. Oh, by the way, wind, if you ever hear this is just a good thing to know. Wind, actually, let me write this over here. Wind, aeolian. An aeolian deposit is a wind deposit, stuff deposited by wind. Okay. All right. By the way, you ever heard of Plymouth Rock? Plymouth Rock, like the Mayflower and, the Pilgrims, all that. Plymouth Rock is, there's a mosquito in here. Plymouth Rock is a glacial erratic. The real rock. There really is a Plymouth Rock. It's a glacial erratic. Okay, so just thought you might want to know. It's kind of interesting. All right, so we are moving along. We've done grain size. We've talked about angularity, sphericity. We've talked about sorting. Let's talk about chemical maturity. What specific minerals, number 8 says, what specific minerals would you expect to find in a chemically mature sedimentary rock? Number 9 says, what does chemical maturity tell you about or indicate about a sedimentary rock? All right. You might remember in the last lecture, we talked about what minerals kind of like break down most easily, what minerals are more resistant to weathering. All right. I showed you kind of a list. There it is, right? Halite, calcite, olivine, calcium-rich plagioclase, and pyroxene are really very susceptible to weathering. Amphibole, sodium plagioclase, biotite, orthoclase, feldspar, muscovite, these are things that are kind of like medium. And these are very, what's a good word to say? Maybe, I guess just least stable, right? And then clay, quartz, gibbsite, I hardly talk about gibbsite, hematite, iron oxide, these are highly resistant. Okay, so when you see a rock and you look at it and it's got mica, it's got quartz, it's got plagioclase, it's got amphibole in it, it's got other stuff, I don't know what that's supposed to be. That means it's chemically immature. Chemically immature. It's got all sorts of junk in it. And that means that it has not experienced very much weathering and transport. Because during transport, all that other stuff, all that olivine and halite and calcite and other garbage just gets eroded away and weathered away and breaks down and it's gone. When you have a rock, a sedimentary clastic rock, and all it has is quartz, or all it has is hematite, or all it has is clay, that means that, and all it has are very resistant minerals, that means that it's experienced a lot of transport. It's experienced a lot of transport. All that stuff has been broken down and weathered away. All the less resistant minerals have been broken down and weathered away. They're gone. And all that's left is the really hard stuff. Okay? That's chemical maturity. So mature rocks, chemically mature clastic rocks, means they've been subjected to lots of weathering and transport. Okay? So that's what that all means. What specific minerals would you expect to find in a chemically mature rock? You would expect to find clay, quartz, hematite, things like that don't break down very easily. So, this is a beautiful green sand beach. Ooh, isn't that neat? That's in Hawaii. And why is it green? That's weird. I'm not used to seeing green sand. It's green because of the olivine. And you might be wondering, how does that happen? Why is that so rare, Well, it's rare because olivine breaks down so fast. But when the olivine is close to the source like this, it means that there was enough olivine. It didn't have to get transported very far, so it didn't break down, and it was able to form this beautiful green sand. Okay, but that's not normal, and it's not normal because usually when you get sand at the beach, it's come from very far away, and all that olivine's it's just been eroded away a long time ago. What's more normal? Normal is more like when you see like these beautiful quartz sands. This is Sleeping Bear Dunes in Michigan. Beautiful place. If you ever get to visit up there in Michigan, go to Sleeping Bear Dunes. One of the most beautiful places in Michigan. There are a lot of beautiful places in Michigan, but that's one of the more beautiful. But quartz is what's left over. Okay, so it's far from the source. That sand has been transported very far, and all of that immature junk has been eroded and burned away. Okay, so there's a good example. This is what mature sand looks like. This is what immature sand looks like. Okay, you see the difference? Immature sand has a lot of, well, look at it. It's actually pretty interesting. You see a lot of things here. Take a look at this. This is actually a really good picture. Notice that these grains are just, the grains up here, the mature sand, just quartz. There's no heterogeneity. There's not like a bunch of different minerals in it. It's just quartz. Those grains are well rounded and they're well sorted, right? They're all about the same size. Look at this thing that has lots of different stuff. This one down here on the bottom has lots of different minerals in it. There are a lot of different sizes. Okay, so the sorting is kind of just medium. And it also, so it's chemically immature. The sorting is not so good. And also it's more angular. Okay, so all that points to the fact that this was close to source. And this one up here is far from source. Okay. Again, on the test, you could have a picture like this, and I just ask you, tell me something about this. Tell me, how far do you think it's transported, far away or close or what, So get ready for things like that. Okay, so just to kind of recap things, right? What do you get? Close to source, breccias. You get further away, you get conglomerates. When you get further away, you get sand, and then finally, when you get far away, you get mud and silt and things like that. Okay, so and you get smaller and smaller clasts as you get further from the source. You get more spherical and less angular as you get further from the source. You get better sorting as you go further from the source, and you become more chemically mature as you move further from the source. Okay, so that's a recap of all that stuff. All right, now if you turn the page, you go on the back page. Now we're going to talk, finish up here. This won't take as long. We're more than halfway through. We're going to talk about sedimentary structures. So sedimentary structures are kind of patterns or something we might see, structures we might see within the sedimentary rock that can tell us even more information about how that rock formed. Very good example of this, and you can actually see this in some places around here in Texas, are ripple marks. So right here, you take a look. This is beautiful, beautiful sandstone with ripple marks in it. And you know where ripple marks form, right? They form in rivers, or they form in tidal bays. They form at beaches and things like that. So this indicates that, hey, this sandstone here must have formed in water, right? Must have formed either in a river or a tidal flat or a beach. And by the way, we can actually tell the difference. And what's even cooler is the size of the ripples and how far apart they're spaced can even tell us how fast the water was moving and how deep the water was. Pretty cool, I think. So ripple marks, mud cracks, cross bedding, graded bedding, trace fossils. We're going to talk about these things just a little bit. We're not going to spend a lot of time on each of these, so it should go pretty fast. But sedimentary structures are features imprinted in the sediment, so this is number 10, during deposition that reveal something about the depositional environment or the bedding. Okay. So like I said, fossil marks can tell you a lot. They can tell you, they're probably the most common sedimentary structure. They can be preserved in the rock, and they can tell you all sorts of things. They can tell you what direction the water was moving in, if it was a river. So if the ripples are asymmetrical like this, it can tell you that the water was flowing a certain direction. If they are symmetrical, if the ripples are symmetrical, it means the water was moving back and forth like at a beach, like where you'd have water, waves coming in and going out and coming in and going out. So it can tell you if it was a beach, it can tell you if it was a river environment. If it was a river, it can tell you what direction the river was going. Okay, so that's what you have to do for number 11, right? You have to say which of those diagrams shows a current, and the one that does show a current indicate the direction of water movement. Okay. Mud cracks. Boy, we have a lot of mud cracks in Corpus Christi. We have a lot of mud in Corpus Christi, and then when it dries out, it cracks, right? So those are cracks left in mud by drying out, by desiccation. So you've probably seen places here in Corpus that look like this, right? Where you go out, there's a mud flat, and it's dried out, and it's all cracked up like that, right? So that forms and can be preserved in the rocks. So it shows you that it can show you a few things. It can show you, that, okay, this was like a dry lake bed, or maybe a floodplain, or maybe like a tidal flat. So it can kind of tell you what the more specific environment was. It can also show what direction was up, which is useful because, rocks are, you're going to see when we cover deformation, rocks get tilted. Sometimes they get tilted all the way upside down, and you don't necessarily know what direction was originally up. So it could be very, very useful showing what direction was originally up. And by the way, you can have mud cracks that can be preserved as a mold or a cast. So see how these are a cast. See how these are like the cracks are actually like sticking up instead of being a crack and going down. So it can be preserved either way, right, as a cast or as a mold. So another thing is cross bedding. Cross bedding forms from sand dunes. Okay, so can you see like these lines that are going kind of like at different angles like this? That's called cross bedding. Okay, cross bedding is really cool because it actually preserves the direction. It forms from sand dunes. Okay, so it screams sand dunes when you see it, and it tells you what the direction of the wind was at the time. So isn't that cool? You can actually figure out what was the direction the wind was blowing during that time. And when you see them forming at different angles, like in this picture, it means that there was a change in the direction, the kind of prevailing direction of the wind, over the years, so maybe for 1 million years it was going this direction, and then suddenly after that it started changed. Why did it change? So we can get all this interesting information about wind direction millions and millions and millions of years ago. I think that's just so cool. Like, how would you have any idea? You might think, how would you have any idea what direction the wind was blowing during, the Mississippian? Well, we can figure it out. So grains pile up on a dune. They pile up on top of each other, right? And then once they get so high, they tumble down, and you get these lines preserved in the rock. So when you get cross bedding, that kind of looks like this. The way I kind of remember is that all of these layers are sort of tilting towards the direction of the wind. Okay, so when you look at number 13, you have to indicate with an arrow what the direction of the wind was. Okay, so just remember that those layers, the cross-bedding layers, are kind of tilting towards the wind. Okay, so right, so you can see that here in this one. See how so you can see how these layers here are tilting towards the wind direction. Okay. All right. Here's just more pictures of cross bedding. Okay, I'm just seeing if I want to say anything about this. Oh yeah, so this is showing, this little GIF is trying to show you how cross beds form. You can see that the cross bedding direction, again, it's tilting towards the wind direction. All right, graded bedding. Graded bedding is when you see these varying kind of periodic layers in the beds, where you go from large size grains to progressively smaller ones. So if you take a look at this closely, take a look at the picture closely, you'll see that you get kind of like large grains up here and then smaller, progressively smaller. And then you start over. You get large grains here and then again gets progressively smaller. And then you get large grains here and then smaller, large grains here and then it gets progressively smaller. So that's called graded bedding. It means it's graded from, large to small. The large stuff on top. Here's that pesky mosquito. I think I got. No, I don't know. I think he got away. Okay, so that's graded bedding. Graded bedding forms from either landslides or more often it forms from turbidity currents. Turbidity currents are like underwater landslides that occur quite a bit right off the coast, like near the coast in the marine settings, so like in the ocean, right? We don't usually see these sorts of things because they're happening underwater, but they're very common occurrences. And again, if you see graded bedding, it means probably it formed from a turbidite, from a turbidity current underwater. So it would indicate like this is an environment. If you find graded bedding, it means this is an environment that was close to the coast in a marine environment near the continental slope. Okay, so that's what that means. Final thing we can maybe talk about here are trace fossils. Trace fossils are marks, tracks, burrows, things that are left over by life. So snail tracks, fossilized dinosaur footprints, fossilized worm burrows, all sorts of things. They're kind of little imprints left over from life. And by knowing what animals were there, it can tell us what the environment was. Like, for example, if you find a fossilized dinosaur footprint, that means that was a terrestrial environment, right? It was above sea level. It wasn't probably happening, that fossilized dinosaur footprint didn't form deep underwater in the ocean, right? Probably formed on land. Okay, so those kinds of things can tell us more about what the environment was. Okay, so that's all I have for you. Oh, I was going to talk about, this is one thing that is kind of cool. Fossilized scratch marks. So this is left over from glaciers. When glaciers are running over and flowing over a rock, they can actually polish the rock, and it can leave scratch marks and striations in the rock. And it actually shows you what the direction of glacial flow was long ago in the past. It can also leave these almost mirror-like shine on the rock. So this highly polished rock is from a glacial environment. So those kinds of structures are also sedimentary structures. Tells you something about glacial movements in the past. So that's all I have for you now. Hope you enjoyed the lecture, and take care and have a good week, and let me know if you need any help with the material, and talk to you next time.